Hello everyone, I'm Jin-Soo Jang from Chungnam National University. Today, I'm very pleased to present my recent work, SelMon Reinforcing Mobile Device Security with Self-Protected Trust Anchor. This is a joint work with Brent Kang from KAIST. Modern smart devices provide various options for building security measures. For example, ArmTrustZone is a hardware-based security feature that enables to create a trusted execution environment. In the TE, we can protect the security critical resources and services, such as crypto keys and operations. Besides, virtualization technique is also utilized for security purposes, because the virtualization, in essence, can isolate the memory using hypervisor-managed page tables and trap the critical instructions. We can create hypervisor-based trusted execution environment. Both the TrustZone and hypervisor have higher privilege than normal application and OS. In addition, under the proper settings of those privileged components, the less privileged and potentially malicious components cannot directly access them. Therefore, they play roles as the trust anchor for building security measures. Let's take a look at ARM architecture with supported processor modes. With TrustZone enabled, the system can have two states, the non-secure and secure states. In the non-secure states, we have user, kernel, and hypervisor modes, and the hypervisor has the most privilege. In secure states, user, kernel, and monitor modes are available. In particular, the monitor mode is a gatekeeper between the non-secure and secure states and has the most privilege in the entire system. In general, the hypervisor, monitor, and secure kernel modes are utilized as trust anchors for hosting system-wide defensive measures, such as the OS kernel integrity monitor. Let's look at the use case of trust anchor, the kernel integrity monitor. It is already deployed on various production smart devices. The integrity monitor aims to protect the OS kernel's static regions, such as code and data. High-end devices generally enable the MMU, so the static region is mapped by page tables for the virtual to physical memory translation. Then, the base address of the page tables is pointed to by the page table base register. The page tables and base registers are managed by the OS. On the trust anchor side, the monitoring agent and trust anchor specific components such as the exception vector and trust anchor managed page tables are hosted. Let's look at how kernel integrity is protected by trust anchor. For the protection of OS integrity, the static region is set to read-only by setting the page tables. Then, to prevent the attacker from manipulating the page tables, for example, making the static region writable, the memory that contains the page tables are set to read-only as well. The attacker can create a malicious page table that maps the kernel with writable permission and try to update the page table-based register to remap the kernel. To prevent this attack, all the security critical instructions that update the page table-based registers are replaced with special instructions that switch the processor mode to the trust anchor mode. By doing so, the OS kernel is deprivileged, so it cannot update the page table as well as the base register. Then, the remove functionality of OS kernel is securely supported by kernel integrity monitor running the trust anchor. For example, when the OS needs to update the page table, it sends a request to the trust anchor. Then, the trust anchor verifies the request and updates the page table. For the context switch, the OS requests the trust anchor to update the page table base register. Then the base register is securely updated by trust anchor. As a result, deprivileging the kernel and verifying and emulating the security critical operations is the key technique of trust anchor-based kernel integrity monitor. Although the trust anchor and its security operations are isolated from the potentially malicious kernel, it is still possible to attack the trust anchor. For example, Google project team showed how the hypervisor-based kernel integrity monitor can be compromised. As can be seen in the example use case of trust anchor, the communication channel to the trust anchor still exists for supporting the OS operations. The attacker can exploit the channel to find and exploit the vulnerability in the software running as a trust anchor. In particular, malicious payload can be sent to the trust anchor. For example, if the page table update function has a vulnerability, the attacker can send the update request with a malicious payload to exploit the vulnerability. Unfortunately, there is no privilege separation in the trust anchor. Thus, once the attacker compromises one of the trust anchor services, it can readily compromise the entire trust anchor. So the research question arises, do we need additional more privileged trust anchor to protect the less privileged one? To answer this question, various approaches for achieving privilege separation of trust anchor have been proposed. They in common partition the monolithic trust anchor software to isolate the critical code and data. For the isolation, they utilize several system features such as system-wide write protection, address translation, and dynamic configuration of virtual address range. Unfortunately, because those approaches require architecture or CPU mode specific features and also entail some attack vectors, we cannot generally adopt them to protect the trust anchor on high-end mobile devices. Please refer to our paper for more details. To address the security problems derived from the absence of privilege separation in trust anchor, we propose SelMon that enables the intra-region privilege separation and self-protection. We logically separate the privilege of a monolithic trust anchor into two regions, the privileged and non-privileged. In the privileged region, we place the critical operations and resources that can be abused by the attackers, such as page tables and instructions that manage system registers. On the other hand, the non-privileged region performs primary operations of a trust anchor, such as the OS kernel integrity protection that is not security critical in terms of preserving the trust anchor integrity. To protect the privileged region from the non-privileged region, which is potentially malicious, we utilize the general hardware features. Specifically, the debug watchpoint and data execution prevention, DP, are utilized to enforce the non-accessibility and non-executability of the privileged region respectively. We apply SelMon to the kernel integrity monitor implemented as a tiny hypervisor to show the feasibility of our approach. Thus, in the following slides, the hypervisor indicates the trust anchor. From now on, I will explain how it works. In our POC implementation, the non-privileged region performs the operations for monitoring OS kernel, and it can be vulnerable. The operations of general kernel integrity monitors, such as updating OS page table, are performed in this region. In the privileged region, we first deploy the gate code, which handle the entry to and exit from the hypervisor and entries to each region. Those gates are mapped in the memory with read-only and executable permissions. Besides, these gates are always accessible and executable during the hypervisor mode execution. In addition to the gates, we isolate the critical resources and operations like the hypervisor relevant page tables and their updates. Note that the code performing such operations are mapped with writable permission. The reason for this will be explained later on. Let's look at how the region and mode switches are handled. First, we assume that the OS is running in the kernel mode. Then the switch from the kernel to hypervisor is conducted by a predefined way, which is invoking a hypercall. The hypercall generates an exception, and it is trapped by the entry gate to the hypervisor that is part of the exception vector. The entry gate first saves the OS kernel's context and watchpoint configuration. Then it configures the watchpoint to monitor the entire privileged region. At this point, the watchpoint is not activated. Also, the gate checks the request from the OS to dispatch a proper trust anchor service. To handle the requested service, the region needs to be switched to non-privileged region. This switch is handled by the entry gate to the non-privileged region. Before entering the non-privileged region, the privileged region should be isolated from the non-privileged region. This is achieved by setting the watch point and DP that enforces the writable region to be non-executable. Note that the monitored region by watch point is already set by the entry gate to the hypervisor, so the entry gate to the non-privileged region simply activates the watch point monitoring. Besides, it activates the DP to enforce the non-executability of the privileged region. Activating watch point makes the privileged region non-accessible, and enabling the DP enforces the privileged region non-executable because the privileged code is mapped with writable, as already mentioned. After isolating the privileged region, we can execute in the non-privileged region to provide the requested service from OS. Here, we assume the non-privileged region updates the OS page tables. Updating the page table of OS sometimes requires the hypervisor page tables to be updated as well. This is because the OS memory should be mapped to the hypervisor. Because the hypervisor's page table is classified as critical resource, it is isolated in the privileged region. As a result, the privileged region needs to handle this update, which requires the region switch to the privileged region. In our work, we utilize the hypercore to switch from the non-privileged to the privileged region. Regardless of where the hypercore is executed, an exception occurs. This exception is trapped by the entry gate to the privileged region that is part of the exception vector. Note that any exception occurrence automatically deactivates the watch point, so the privileged region is set to accessible. The entry gate deactivates the DP to make the privileged region executable. Now the control flow can move to the privileged function that manages the hypervisor's page table. Once the privileged function is completed, the control flow can move back to the non-privileged region, or the CPU can switch back to the kernel mode. In this example, we assume that the hypervisor finishes providing the requested service, so the OS will take over the control. To handle the CPU mode switch, the exit gate from the hypervisor is invoked. The exit gate restores the saved OS kernel context and watchpoint settings and switches the CPU mode to kernel. Finally, the OS can continue to execute from the point preceded by the hypervisor invocation. Although SelMon effectively isolates the privileged region, there still exist several attack surfaces that can be abused by the attackers to bypass SelMon. First, as the non-privileged region is untrusted, the attacker can attempt to inject malicious code or reuse the available instructions in the non-privileged region. However, because critical instructions that can be abused by the attackers are classified and removed from the non-privileged region, the attacker cannot find meaningful instructions for disabling SelMon. Injecting a malicious code to trust anchor requires updating page tables to add executable permission to the writable memory. Because the hypervisor managed page tables are also isolated, this attempt is simply prevented. The attacker can try to abuse the gate code that is always exposed to handle the region and mode switches. Those gates entail critical instructions that manipulate system registers for the DP and watchpoint configuration. To prevent this, we put some validation logics after updating the system registers. Because the value for the update is predefined and constant, we can readily verify the legitimacy of the updated values. Lastly, because the attacker has the trust anchor privilege even in the non-privileged region, he can try to find usable instructions available in OS and execute them with a trust anchor privilege. Hampering this attack is straightforward. We simply map the OS kernel region with no execution permission in the trust anchor's page tables. Thus, during the trust anchor execution, the less privileged software, such as OS, is not executable. To evaluate the performance of SelMon, we measured the latency of basic OS operations on two different environments, OS with original and SelMon hardened hypervisors. The overhead with operations in the first four rows, such as Cisco read and write, was negligible. However, creating and executing a new process in the last three rows imposed maximum overhead of 32%. Because the overhead depends on how frequently the hypervisor is invoked for page table update and context switches, we can infer that the last three cases more frequently interact with the hypervisor. Besides, we observed maximum overhead of 2% and 5% with spec and photonics benchmarks. In this evaluation, most of the SelMon overhead was obscured due to the longer runtime compared to that of Adam Bench. In conclusion, we utilize the general hardware features to protect the trust anchors on modern smart devices and propose an intra-region privilege separation mechanism and show the feasibility of our approach by hardening the hypervisor-based kernel integrity monitor. Thank you for listening. I'm happy to take any question or comments.